Gravity is capable of holding many things together. The planets and stars themselves, their orbits, such as a moon around its host planet, or a planet around its host star. It also holds together the solar systems orbiting around these stars, but it can go beyond this as well, holding together even galaxies themselves. Galaxies consist of stars, planets, and expansive clouds of gas and dust, all of them bound together by gravity. They can come in a variety of sizes too, with the biggest of them containing trillions of stars and spanning to be more than 1,000,000 light years across, while the smallest only contain a few thousand stars and span just a few hundred light years. Most large galaxies also have a supermassive black hole at their centers, some of them having billion times the mass of our sun. Our solar system is part of a galaxy as well, which you most likely have heard by the name of the Milky Way galaxy, though certainly not because of the chocolate bar. Our galaxy is about 100,000 light years across and contains nearly 100 billion stars. In fact, most of the stars we see in the night sky are in just one of the Milky Way's arms. Now, our solar system sits about 26,000 light years from the center of our galaxy, and it takes us 250 million years to revolve just a single time around the galaxy's center, where our supermassive black hole, Sagittarius A star, resides. Let's take a look at how it and galaxies in general form. Like with many things in the universe, it all began with clouds of gas and dust, which started collapsing on each other, getting pushed together by gravity. In the case of the Milky Way, this happened roughly 13.6 billion years ago, and it first led to stars forming from these collapsed clouds. We see these today in globular clusters. Soon after this, the spherical halo emerged, followed by the flat galactic disk. The galaxy started small and grew from there as the inescapable force of gravity pulled everything together. As for how the Milky Way evolved fully into what it is today, this is still a mystery, which has led to something called galactic archaeology, which aims to unravel this mystery. One mission that seeks to help us with this is ESA's Gaia mission, which released its first catalog of data in 2018. What Gaia does is measure the exact position and distances of more than 1 billion stars, along with gathering their light spectra. This lets scientists understand their composition and age. According to ESA, this position data also allows astronomers to determine the speeds and directions that the stars are moving. Because things in space follow predictable trajectories, astronomers can reconstruct the path of these stars billions of years into both the past and the future. By combining these trajectories into one stellar movie of sorts, we can capture the evolution of the galaxy over eons. As we gather more data, I am sure we will learn more and more about our very own Milky Way galaxy's formation. Once formed, galaxies like our own come in a variety of shapes, mostly spirals, ellipticals, and lenticulars. But there are ones with less orderly appearances too, which we usually call irregular galaxies. To give a quick example here, our Milky Way galaxy is classified as a spiral galaxy. The spiral galaxy is defined by the presence of spiral arms. They resemble giant rotating pinwheels with a pancake-like disk of stars and a central bulge or concentration of stars, right near the center. The spiral arms can be wound tightly or more loose, And some of them cannot be seen from Earth because we view the galaxy from the side. Spiral galaxies are surrounded by halos, mixtures of old stars, star clusters, and dark matter, which I cover in my video here. The youngest stars form in gas-rich arms, while older stars can be found throughout the disk and within the bulge and halo. Both the Milky Way and our neighbor, the Andromeda Galaxy, belong to a subtype known as barred spirals, which make up about 2/3 of the group. Barred spirals support ribbons of stars, gas, and dust that cut across their centers. Scientists think that the presence of a bar indicates that a galaxy has reached full maturity. Now, elliptical galaxies, such as NGC 2865, shown here, have shapes that range from completely round to more oval. They are less common than spiral galaxies, and unlike spirals, elliptical galaxies usually contain little gas and dust, and they show very little organization or structure. The stars orbit around the core in random directions and tend to be older than those found in spiral galaxies. Since little of the gas remains to form new stars, scientists think that elliptical galaxies originate from collisions and mergers with spiral galaxies. Which then brings us to lenticular galaxies, such as NGC 4886, which are a cross of sorts between the previous two, spirals and ellipticals. They have a central bulge and disk, common to spiral galaxies, but no arms to speak of. Then, like elliptical galaxies, lenticulars have older stellar populations and little ongoing star formation. We have a few theories about how this type of galaxy has evolved, and one such idea suggests that these galaxies are older spiral galaxies whose arms have just faded to time. Another idea proposes that lenticulars formed from mergers of spiral galaxies, such as what will eventually happen between the Milky Way galaxy and the Andromeda galaxy. And then, like with many things in the world, or in the universe, there are some galaxies out there that just don't really fit in with any of these. And these are the ones that are known as irregular galaxies. This type has unusual shapes like toothpicks, rings, or just little groupings of stars. They range from dwarf irregular galaxies, such as NGC 5264, shown here, with 100 million times the Sun's mass, ranging up to larger ones weighing 10 billion times the Sun's mass. Astronomers think these galaxies' odd shapes are sometimes the result of interactions with other galaxies. As an example, one spiral galaxy passing by another spiral galaxy which has a stronger gravitational pull than it could end up causing the lighter one to lose some of its material, then become distorted and start morphing into a new shape. Others, like gas-rich dwarf galaxies, may just be new, formed by material pulled from such encounters. Or it may even be that when galaxies collide, they create a larger, strangely shaped mashup. Another theory out there is that some irregular galaxies could represent an intermediate step between a spiral galaxy and an elliptical galaxy. Irregular galaxies that were born from galaxy interactions or collisions, as you may expect, tend to host a mix of old stars and younger stars, depending on the characteristics and composition of the original galaxies, of course. Irregular galaxies may also end up with significant amounts of gas and dust, which could then lead to new star formation as well. There are some galaxies in our universe that are still active, around 10% of the ones we know about anyway. Now at this point you may be wondering, what exactly makes a galaxy active? What this means is that their centers appear more than 100 times brighter than the combined light of their stars. They can be spiral, elliptical, irregular, and I'm sure lenticular too. Our Milky Way does not fall under this category as it is no longer active, although it did likely experience a burst of activity in the past, roughly a few million years ago. Where does the excess energy that makes a galaxy active come from? Currently, astronomers think this excess energy comes from areas near the galaxy's central supermassive black hole. Gas and dust begin to collect around the black hole and form an accretion disk. And the black hole's gravity then compresses and heats this disk, which causes the material to glow across multiple wavelengths, spanning from infrared to X-rays. But I wouldn't even be surprised if it goes up to gamma rays too. Speaking of infrared, observations made in this wavelength show us that a black hole and its accretion disk are embedded within a clumpy ring of cooler dust. This ring is called a torus, and it may be a few light years across in size. Close to the black hole, though, a small fraction of the infalling gas can also end up getting driven outward, perpendicular to the disk, as jets of particles that move near the speed of light. These characteristics would come to help us categorize active galaxies based on their distinctive characteristics. And we also learn that our viewing angle, such as seeing directly into the torus or seeing it from the side, may be part of producing these characteristics that we pick up on. While galaxies are among the oldest objects in our universe, some of them are also rather young. Most of them are between 10 to 13.6 billion years old, reaching almost back to the point of the Big Bang, while the youngest ones may have formed as recently as 500 million years ago. They are also among the largest objects that exist in space, so it is impressive to me that we are able to study them so in depth. With so many of them out there in our universe, aside our own Milky Way, we do certainly have quite the sample set to pull from. So, did you have a favorite thing I talked about today? Or do you have a favorite galaxy in our universe? I would love to hear more about it in the comments below. And as always, I hope you learned something, and I implore you to step outside tonight and look towards the stars.